If you wanted to simulate the universe in a computer, the information you would need to enter is first, all the laws of physics, the initial conditions of the universe, and about 26 fundamental constants. These constants are needed in order to describe the universe as best we know it. And if you did this and let the program run, you would end up with a universe which would pretty much look identical to what you see all around you. We're familiar with the laws of physics, but what are these 26 fundamental constants? These are constants that have to be measured and are what they are. There is no current theoretical basis to predict what these should be. The first 15 of these are the rest masses of the fundamental particles of the Standard Model: 6 quarks, 6 leptons, and 3 bosons. 4 of these numbers are the quark mixing parameters. These are required to describe the weak nuclear force and nuclear decay. Another 4 numbers are the neutrino mixing parameters. These describe how neutrinos mix with each other. There is the cosmological constant, which describes the amount of acceleration present in the universe's expansion. The fine structure constant, which represents the strength of the electromagnetic interaction. And finally, the strong coupling constant, which defines the strength of the strong nuclear force involved in keeping neutrons and protons glued together in the nuclei of atoms. But you'll notice that these constants all apply to some kind of object in the universe and how these objects interact with each other. They do not apply to all things everywhere. So perhaps they're not so fundamental in that sense. There are, however, 4 special constants that apply to everything everywhere. So these may be the most important numbers in the universe. And what these constants reveal about the universe is rather astonishing. What are these special constants, and what do they tell us about the universe in which we live? That's coming up right now. Before we get into the incredible story of the constants of the universe, let me tell you part of my inspiration for making this video. I watched an 8-episode series on Magellan TV, today's sponsor, called The Secrets of the Universe. This series looks at some of the strangest phenomena in the universe using some superb graphics and supercomputer simulations. Magellan is a new kind of streaming documentary service founded by filmmakers and producers who bring you the best documentary content. Featured subjects include history, nature, technology, and of course science. You can watch it on any of your devices, and if you enjoy 4K, you're going to love their library. Magellan has a special offer for Arvin Ash viewers. If you click the link in the description, you'll get a free 1-month trial. If you want to support this channel and enjoy Magellan TV, then be sure to click the link in the description. Consider the simplest atom, the hydrogen atom. It consists of 1 electron and 1 proton. To describe its interactions, at a minimum, you have to know a few of its properties. These would be properties such as the fundamental charge of the electron, the charge of the proton, the mass of the electron, the mass of the proton, and the strength of the electromagnetic force. These can all be found from the fundamental constants. Fundamental constants means they are measured properties because we do not currently have any mathematical model that predicts exactly what these numbers would be. So these cannot be derived, they have to be measured. This is not to say that some mathematical model doesn't exist which could predict these numbers, but it does say that we currently do not know what such a theoretical model is. It is possible that a future theory of everything, perhaps something like string theory, would predict these values. Now, if we go back to the same hydrogen atom model, in order to model its behavior even more precisely, we would have to take a few other fundamental constants into account. The electron and proton, for example, have rest mass. Therefore, they would gravitationally attract each other proportional to the gravitational constant g. This gravitational constant appears in both Newtonian gravity and general relativity. It can be thought of as the proportionality factor between the strength of gravity and the masses creating that gravity. Since gravity applies to everything everywhere, g is the first of 4 constants that is universal. It has units of length cubed divided by mass times time squared. The electron and proton would attract each other proportional to the permittivity of free space, epsilon naught, because this permittivity is the electric constant based on James Clerk Maxwell's equations. And since the electron is spinning, it would have a magnetic moment proportional to the permeability of free space, mu naught, because it is the magnetic constant also according to Maxwell's equations. Mu naught and epsilon naught are properties of space and are constants that have to be measured. There's no theory that predicts their values. Turns out that mu naught and epsilon naught determine the maximum speed of light in the universe. This was found by James Clerk Maxwell as well. The speed of light is a very interesting constant. One way to think of it is as a conversion factor between mass and energy, as found by Albert Einstein in his famous equation E equals mc squared. But it can also be thought of as a conversion factor between the time dimension and the three spatial dimensions of our four-dimensional universe. C also applies to everything everywhere and is the second of four universal constants. It has units of distance over time. Another constant which applies to everything is H, Planck's constant. It is the fundamental constant that sets the minimum scale of quantum phenomena. It can be found in just about any quantum mechanics equations, from Schrödinger's equation to the QED Lagrangian to the Dirac equation. It is associated with quantum states and transitions of quantum states. Planck's constant has units of mass times distance squared divided by time. Finally, there is Boltzmann's constant, which also applies to everything. It plays a role in determining the amount of vibrational energy contained in an atom related to temperature. It is just the definition of the energy contained in 1 degree Kelvin. It is in units of energy per degree. And using just 3 of the 4 constants, G, C, and H, we get some extraordinary insights into the nature of the universe. So for example, if we take these 3 constants and manipulate them mathematically like this, we get a length. What is this length? Well, this is the Planck length. It is the minimum length that would be meaningful in quantum mechanics. Similarly, by manipulating these constants mathematically, we get time. What is this time? This is the Planck time. This is the minimum time that can exist that would be meaningful in quantum physics. We can also get energy by rearranging some of these constants. This is the Planck energy. This is the maximum energy that could be contained in a cube that had the size of 1 Planck length. We can convert this Planck energy into mass by using Einstein's famous equation E equals mc squared. This represents the maximum mass that a cube of 1 Planck length could have. All these are values for the Planck scale. This scale really applies to everything in the universe. The units of these scales may be the most natural units for measuring things. Since these numbers are ubiquitous in physics, physicists often just use what's called natural units and set these 3 constants equal to 1. But what is the significance of the Planck scale? The Planck length is the shortest length that means anything in the equations of quantum mechanics. This is not to say that something smaller doesn't exist. For example, the singularity at the center of a black hole is supposed to be an infinitely small point with infinite mass density, but Planck length is the smallest unit that we can measure. It is the smallest scale that we can theoretically probe with particle accelerators. These scales are the theoretical limit, but in fact, it is many orders of magnitude smaller than what we can practically measure today with the most powerful accelerators like the Large Hadron Collider. The Planck length is fundamental. So for example, if string theory is true, then the strings would presumably be as small as the Planck length. Any smaller, and they could not be defined in physics. This would also be the smallest size of the loops in loop quantum gravity. And these strings would vibrate at minimum timescales of the Planck time. In loop quantum gravity, the movement of the spin network would occur like a digital clock in increments of Planck time. Planck time is the time it takes for light to travel 1 Planck length. It is the smallest measurement of time that has any meaning in quantum mechanics. Planck time is the closest time to the beginning of the universe, occurring right after the Big Bang, that we could theoretically model. This would be around the time that all 4 fundamental forces were 1, just shortly before gravity separated out and became a distinct force from the other 3. We have no idea what occurred prior to this time, nor do we have any model for what could have occurred. Using the word before may in fact be meaningless because time itself started at this point. This would be the true beginning of creation. Even though we have no model for what occurred or what may exist at scales smaller than the Planck scale, many people, including scientists, speculate what that could be. For example, it could be a kind of quantum foam where gravity could fluctuate or be in superposition. Perhaps this is where gravity and quantum mechanics unite somehow. Or it is possible that space-time itself is quantized at this level and there is nothing smaller than this. Could space-time be in superposition like other quantum phenomena? Perhaps, but this would violate some of the current understanding of gravity. Quantization of spacetime at these scales is the kind of universe that the theory of loop quantum gravity implies. What about Planck energy? If the Planck energy was confined to the volume of a cube the size of one Planck length, it would form a black hole. The Planck mass is considered the smallest possible mass that a black hole could have. If we could create a black hole like this in a particle accelerator, it would have gravitational effects at the quantum scale, and we could perhaps crack the holy grail of physics by understanding how gravity works at quantum scales, and finally come up with a theory of quantum gravity. If we actually built an accelerator that achieved the Planck energy for a particle like an electron, a black hole would form. So it would not help to go to higher energies than that, since the black hole would just get bigger, and there would be no information that we could attain. This is why the Planck length is the smallest length scale that we could theoretically probe. Note that Planck energy converted to Planck mass is really a lot of mass packed into a very small space. This is why black holes form. The mass is equivalent to about 1% the size of a mosquito. Although this sounds really small, it's really large in energy terms. In fact, this mass converted to energy is equivalent to the energy contained in a tank of gasoline or petrol in your car. When you pack that much energy or equivalent mass to a size as small as the Planck cube, you get a black hole. This is a pretty large amount of mass for such a small volume. Why is this the case? You have to remember how weak gravity is. It's the weakest force in the universe. It's 10 to the 39 times weaker than electromagnetism, for example. And because it's so weak, we have to pack a lot of mass for the gravity to be strong enough to form a black hole within that volume. Now, some people have used the precision of the various constants to argue for fine-tuning. This is the claim that conditions which allow life in the universe lie within such a narrow razor's edge that any slight variation would have resulted in conditions which would either not have created matter or large astronomical structures like solar systems or complex compounds or life as we know it. And some argue that the chances are so small that we must live in a simulation where these precise constants were entered into the program, or that a supernatural being, God, must have chosen the constants so that life could exist. Others counter this argument by saying that the universe isn't all that fine-tuned for life because, by all accounts, almost all the volume of the universe supports no life. There's only a limited number of planets in a limited number of solar systems that are within limited distances from their stars with specific combinations of compounds, namely carbon and water, that are conducive to life as we know it. But if you look at the vast number of planets available in the universe that nature has to work with, there's bound to be life on some of them. Or that the constants are but one variation in a vast multiverse of universes, and life in a different form could exist with a different set of constants. None of these claims is currently falsifiable. Any way you look at it, I think we have won the cosmic lottery. The big question is, how many tickets did we buy? And how many simulations did our overlords create? I'd like to thank my generous supporters on YouTube and Patreon. If you like my videos, consider joining them. And if you have a question, post it in the comments below and I will try to answer it. I will see you in the next video, my friend.